In this second lecture on random variables, we'll be looking at expectations or means. So exactly as we can find mean for data, we can also find the mean of a random variable. Let's have a look at the data situation to start off with, so we can look at something that we've seen before. If I have the following data, 1, 1, 1, 2, 2, 3, 3, 4, 4, 5, and I want you to calculate the mean of the data. So one way of doing this is to simply take a look at what we call a frequency distribution of this. So here is the value of the data, and here is the frequency of the data, and then I multiply the fi by xi and I sum them. So that 1 occurs 3 times, 2 occurs twice, 3 occurs twice, 4 occurs twice, and 5 occurs once. So when I add the numbers to find the average, of course I can do 1 plus 1 plus 1 and so on. But you see I'm adding 1 3 times, and that's what I've got over here. So adding 1 3 times is 3 times 1, the frequency times the observation. That gives me 3. Likewise for 2, it's 2 times 2, 4. And the 3's will add to 2 times 3, which is 6. And 2 times 4 is 8. And 1 times 5 is 5. So I add all this up, I get 10 there, 21, 26. And the number of observations I have here is what I get if I add all these up. There's 3, 4, 5, 6, 7, 8, 9. I've got 10 numbers there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the mean here comes by, the first thing is I multiplied the fi by the xi and I added them all up. And then I'm dividing here by the number of observations in. Now the ends are constant, so I can fool with this a little bit. I can take this as fi over n times xi, and then sum them up. So for example here, if I take a look at this fi over n idea, we call this a relative frequency. This is the relative frequency. In other words, it's the proportion of times my data xi occurs. Relative frequency. So here the relative frequency is going to be fi over n, and here that's going to be, well, I'll just actually translate across here. If I use my fi over n over here, it's 3 over 10, 2 over 10, 2 over 10, 2 over 10, 1 over 10. And you can see if I now do the multiplication, the 1 times 3 over 10, I get 3 over 10. The 2 times 2 over 10, I get 4 over 10. And so on. I get 6 over 10, 8 over 10, and 5 over 10. And so previously my average was going to be 26 over 10. From my numbers here, the sum was 26 and altogether 10. Now this actually becomes 1 because these things all add to 1. And if I just simply add these, fi over n times xi, if I add all these up, I'm going to get x bar as 3, 7, 13, 21, 26, and of course the 10s are constant here, I get 10. So these fi over n are the relative frequencies, and they are all bigger than or equal to 0, and they add bigger than or equal to 0, sorry, and they add to 1. So they actually behave exactly the same as probabilities. They are all bigger than or equal to 0, they add to 1, and the way I find the mean of the data here is multiply by these relative frequencies, which are like probabilities, with the data value and add them all up. So I can use the same idea with random variables. So what I've just talked about there has been listed in this next slide, which I'll go over very fast. So the same idea here. All these are between 0 and 1, and they add to 1, and they behave like probabilities. So if I use the same idea to define myself the mean of a random variable, let's take a look at an example over here. I've got x denotes the number of heads in a single toss of a coin. the probability mass function we saw earlier is either 0 or the values are either 0 or 1, 0 heads, 1 head, probability is 0.5 each for a fair coin. So the mean here should be multiply the value of x with the probability, value of x with the probability, so 0 times 0.5 and 1 times 0.5 and add that up and I get simply 0.5 from here. So this is a long run average. And in fact is saying that if I toss a coin once, I'm getting half head. That's nonsense. Of course, you can't get half a head. But as an average, I'll expect to get half the tosses will give me heads. If I toss the coin 10 times, I expect half of them to be heads. Now there's 5 heads. 1,000 times, I expect half of them to be heads. There's 500 heads, and so on. So this is half of the tosses will give me heads. Or I get heads in half of the number of tosses. So the definition more mathematically is simply, don't be confused by this. All I'm doing is saying, take the value of x, multiply with the probability, and add them all up. That's all. You need to understand how to do the process, not so much actually what the formula is written down is. Now, of course, I can work out other expectations as well. If I've got x squared, you might wonder why I went on the meaning of x squared, but we'll see why later on. Then all I do is I replace the x here by x squared. In general, if I've got something like a function of x, like a gx, this could be x cubed, or square root of x, or x plus 1. It makes no difference. I replace it over here. So whatever I have over here is what I put over here, multiply with probabilities, and simply add them up. That's how I find the means. So here's an example. I have got a probability mass function, negative 1, 0, 1, 2 with probabilities 0.1, 0.2, 0.3, 0.4. I want these particular means. So E of x is going to be simply multiply the value of x with the probabilities. So it's negative 1 times 0, 0.1, excuse me. And then 0 times 0.2, and so on. 1 times 0.3, and 2 times 0.4. So the value multiplied with the probability, the value times probability, and add them all up, and here I'll get 1. If I want E of x squared, all the changes is now I'll square their values first. So it's negative 1 squared, be careful, negative sign is outside the square, 0 squared, then 1 squared, and then 2 squared times 0.4. So here that comes to 0.1. So negative 1 squared is equal to 1, and that's 0.1. This next is 0. This next is just 0.3, and the next is 4 times 0.4 is 1.6. So that gives me 2. Now if I want E of x plus 1, then all that happens now is, as before, I'll be taking a look at negative 1 plus 1 times my 0.1 plus 0 plus 1 times my 0.2, and so on. 1 plus 1 times 0.3, and finally 2 plus 1 times 0.4, and that'll come to 2. So that's how I find means for random variables or functions of random variables. Some notes here. This EX, as we said, is also called the expectation, the mean. Sometimes you'll find words like expected value. All these things mean the same. Expected here means what I would expect, as I say. It's an expectation. It's some kind of average. We also use the symbol mu for mean. So this is read as mu, or if you like, mu with this way. in general, you will find that these kinds of things don't work. E of x squared is different from just taking the mean or E of x and squaring it. They just aren't the same thing. They'll never be equal except in very rare cases, special cases. Some properties of expectations. Again, some of this is going to be mathematical, but we just need to understand the result. If I have a constant random variable, its mean is the constant. Exactly as if I have the data, which is always the same value, all ones in the data, the mean will be just 1. So it's likewise here. If the value of a random variable is just a single constant with probability 1, then it will be just the value of the mean will be just c. If I've got constants a and b and I scale in this way, the mean scales in the same way. So if I take a look at this and multiply it by a and add b, so I'm scaling by a and shifting the mean down, shifting by b, the mean will scale in the same way, exactly the same as with data. If I have two of these things, and if I add them first, I want e of x plus y, then simply I just add the means. And the one other thing is, if I mean shift, in fact I'm taking this and shifting the mean down to 0 essentially, I'm shifting everything down by the mean, the new thing I'm going to get is going to be having mean 0. The same as I had before with xi minus x bar equals 0. So these results hold. So just understand and be able to use the results without actually having to prove them very much. So some proofs here over here just for those who are interested and just to understand also how these things actually can be manipulated. If the random variable is a constant, it takes just the single value with probability 1. It's always the same value. Probability of having c, the value c is 1. And so if, of course, the mean is c times 1, that's just c. To find the next one, I'm going to use properties of summation. So the mean of ax plus b means I have ax plus b there, times the probability mass function. And so I'm going to split this up. It's ax times the probability mass function plus b times the probability mass function. Now, I'll separate this out here. So here the ax times px is one term, and this is another term. I'll break this into two sums. And now in this part over here, this a is a constant, I can take it outside the summation. And here the b is a constant, I can take it outside the summation. This doesn't depend on the x here. Then I've got a times x times px added up, and I've got b times the sum of px. This is just the mean of x, as I've got the e of x. And because here I'm adding probabilities, all the probabilities, that sum should be equal to 1. So this all I get is a times the mean of x, this is the mean of x over here, plus the b. We'll omit the proof of the third one, that's more difficult. But the last one's straightforward as well. I would e of x minus mu x, then I'm going to use my previous rule from 2, and I'll separate these out. So the e of x minus e of mu x. Now e of x, I'll leave alone. This is a constant. It is just, once I've worked out the mean, this is not random anymore. This is a constant, and so the mean of a constant is the constant, and I get mu x here. Now, these two are the same thing with different symbols. So I can write e of x as mu x as well, and that gives me 0. The next thing we look at is variance. Now, the variance is defined in the case of data was this formula there. It's take off the mean, square it, and average it. So averaging is the same as expectations. So I do the same with random variables. I subtract the mean, square it, and average it. This is my averaging, the expectation. We also use the symbol sigma squared x for variance. And the standard deviation is the square root of the variance, and we usually denote that as sigma x. As an example over here, here's my previous random variable I saw before. We had e of x, the mean was equal to 1. So if I want the variance here, it's x minus the mean first. So it's going to be negative 1 minus the mean, and then squared times the probability 0.1. I'm looking at this expression squared, take the mean of it and square it. Then it's 0 minus 1 squared, and then it's 1, take off the mean, which is 1 squared, and then finally 2 minus the mean. Oops, sorry, I should be multiplying with probabilities as I go through, so let me just fix this up quickly. So it's 0 minus 1 squared, probability is 0.2 there, then 1 minus 1 squared, and the probability here is 0.3, and finally it's 2 minus 1 squared, and the probability is 0.4. So let me just add these up. So that's 2 squared, that's 4, that gives me 0.4. That's negative 1 squared, and that's going to be 1 times 0.2. That's 0, so that's going to be 0. Yeah, and this last one is 2 minus 1 squared, that's 1 squared, times 0.4 is 0.4. So I get here, the variance is equal to 1. So that means sigma squared, the mean, the variance of x is 1, and the standard deviation of x will also be 1. So you can see this doesn't take too much work to calculate. Okay, properties of variance here, very quickly. Variance can't be negative, it must be bigger than or equal to 0. If I have a look at the variance formula for the data, remember I had this expression over here earlier, xi minus x bar squared becomes essentially add of the xi squared and then minus n times x bar squared. The same idea works here. Variance of x was x minus mu squared, so it becomes ex squared, then minus the mean all squared. And this is far simpler for actually calculating variances. And the usual idea of scaling, if I scale and mean shift, the shifting of the mean doesn't affect the variance because variance is the measure of spread, and adding a b just shifts everything across, down, or whatever. But the scale factor works. So if I've got something that looks like that over here with that kind of spread, if I move it from 0, for example, somewhere else to b, it doesn't change the spread. But if I scale it, either it goes outwards that way, it spreads out, and that changes the variance, or in other words, it goes flatter, or it is shrunk, and that also changes the variance. So the scaling works in the same way as you'd expect. So the only thing is, because the variances are positive, I'm going to square this, and that's how the scaling works. And I could also write down, for example, if I look at the standard deviation of this ax plus b, then as we saw before, all that will happen is I'll have the a out there, as we'll see soon. So the proof here is very simple for each of those. This part here, variance of x, as I say, is bigger than or equal to 0. If I look at how the variance of x is calculated, it's x minus mu x squared times the probabilities, and I'm going to add them all up. This is a square term there, that's bigger than or equal to 0. These are probabilities, they're also bigger than or equal to 0. Every term in this sum is bigger than or equal to 0, so the whole sum is bigger than or equal to 0. That's very simple to understand. This one here, if I look at this x minus x bar, x or x minus mu squared, this is what I'm looking at the expectation for. If I just square that, that means multiply this with itself. Solve it slowly. So it's the x times all this. It's the x times all this. That's the first term. And there's a mu times all this. That's my second term. And again, I'll break this apart. That's my first term, e of x squared minus x times mu x in the first term. And then the e of this lot over here, this is the constant, so I've taken the thing outside the expectation sign. And then I'm left in the expectation of x minus mu x. And I know that from my earlier rule on expectations, that's going to be 0. So all I've got is left the first term, and that's x squared minus mu x. I separate these again. I've got e of x squared minus this constant comes outside times ex. Now this ex and mu x are the same thing essentially. So I've got e of x squared minus the mean squared. Or if I write the mean as e of x, I get this formula, e of x squared minus the mean all squared. That's a simpler formula for calculating variances. And for this one, it just says the proof is similar. All I do is replace the sigma with the expectation value as I saw with sums. Which is simple, ax plus b minus the mean of ax plus b. So if I just spread this out, I get ax plus b minus a. This is a constant, comes outside. And this is a constant, also comes outside. And I'm squaring the whole lot. Well, if I look at this, you'll find the b's cancel off. And I've got the ax minus mu x squared. And the a, when I square, I get x squared. Now with all this squared, this is the constant, comes outside. And this, what I'm left here is the variance of x. And so I get a squared variance of x. And so the standard deviation of ax plus b is just a times the standard deviation of x, except I'm going to make sure the a is positive, so I take absolute values of that a to make sure. So if I've got something like sigma of negative 2x plus 4, that will be negative 2 absolute value of times sigma of x, and the absolute value of 2 is just 2, I get twice sigma of x. Okay, let's take a look at an example. A company has to complete a project no later than 3 months from now, or there will be heavy cost overruns. So given the timings of scheduled work, the manager of the construction believes that the job can be finished in either 2.5, 3, or 3.5 months. They usually work in 2-week periods from now, with corresponding probabilities as given there. We're going to find the expected completion time and the variance, and we're going to interpret these as well. So the first thing is to get the probability mass function. So the random variable here is going to be x. It denotes the time to complete the project. So as in probability before we defined events, now we define random variables. I'm looking at the time to complete the event, the project. So the values here we've given is 2 months, 2.5, 3, 3.5 months. Probabilities are 0.1, 2.4, and 0.3. So the first thing was to get the random variable and then the distribution. Before we were looking at the event and the probabilities, so it's random variable and the probability mass function distribution. Now I want to find the mean and variance. So I can almost do the thing over here. Sorry, too far. So E of x over here, the mean, is 2 squared times 0.1 plus 2.5 squared times 0.2 plus 3 squared times 0.4 and then 3.5 squared times 0.3, and so you can calculate that, and what you'll get is, that's 2 squared is 4, so that's going to be 4.4. The 2.5 squared is 6.25, and if I multiply with 0.2, 6.25 becomes 12.5 is 1.25. You can check my calculations. 3 squared is 9 times 0.4 is 3.6, and 3.5 squared times 0.3, so this is actually 12.25 times 0.3. You'll find this comes to, I see I've just been doing e of x squared actually, sorry, so let's actually put a of x squared there anyway. Let me work with the x squared first. So this should come to, you'll find the numbers work out to be 8.925. And so over here, e of x will be simpler, of course, it will be just x times the values. So it's 2 times 0.1 plus 2.5 times 0.2, and then so on. And that comes to 2.95. So the variance over here of the time to complete this project is going to be e of x squared minus the mean all squared. So e of x squared was 8.925. And the mean is 2.95. Square that and calculate that. And if I do that, what I'll get for the mean and for the variance is that comes to 0.225. Now, variance isn't such a good measure of spread because it's in square units. So this is a square months over here. But if I look at the standard deviation, which is the square root of this, this comes to 0.4717, and that's in months. That makes much more sense. So what I've got here is the mean time to completion was 2.95 months, and the standard deviation of completion is 0.47 months. Now the question says that no later than 3 months. And so the mean here is almost 3 months as it is. And I've got a standard deviation here of about half a month. So it's very likely, because looking at how data behaves, if the mean is about 3 months and there is a standard deviation as well, I'm likely to be will be above that quite often as well. So here, the project is very likely to exceed 3 months. So the manager can expect that there will be some extra costs involved in this. So this is exactly the kind of calculations we expect to do in these situations, but also we can interpret them and get some meaning from them. The last part is standardized random variable, and this is what I'm looking at. I have taken the mean off, subtract the mean, and divide by standard deviation. We call this standardization because I've shifted the mean to 0, so this is essentially what we call, now I've taken the mean down to 0. And if I divide by the standard deviation, I've scaled the standard deviation now down to 1. So you'll find what will happen over here is, you don't have to follow the mathematics, but the basic idea here is this. What I've got here is a random variable that now has e of z, the mean is equal to 0, and the variance of z is equal to 1. Now, those of you who might have done some work with normal distributions will find that that's what we do all the time in the situation. So this is where they'll be mainly used. But for the moment here, we'll need to look at this and just quickly understand what's going on here. What I've done is I've taken the mean down to 0, shifted the mean to 0, and scaled the standard deviation of variance down to 1 by doing this transformation, x minus mu over sigma. As a note over here, as I was saying earlier, if I've got y equals ax plus b, the variance scales with the square, and the standard deviation is going to be the same scale as the way I scale random variable, except I want absolute values to make sure this remains positive. So that finishes our work on random variables so far. We'll take a look at two special distributions, the Poisson binomial and Poisson inverse order, in the next lecture. Thank you.